Okay, we now want to find the capacity of the additive Y Gaussian noise channel. Okay, C is the capacity of the channel. Here, the maximization is done over the input symbol distribution Px. Okay, and then it has a constraint that the expected value of the symbol, input symbol x power, x square is equal to c, equal to p, okay? And this maximization is for mutual information, as we have done, and mutual information between input and output of the channel is hy minus hy given x, and the hy given x can be written hx plus z given x. Since x is given, there is no uncertainty, and differential entropy is a translation invariant, so we can say it is hz. And the hg in chapter 8 we have calculated, that is half log 2 pi e and sigma square, but in this case the sigma square is the noise power n, capital N. So that's the hz. And h of y is a continuous random variable y. The y has power which is ex square plus z square. So expected value of x square is p. Expected value of z square is n. So here I think I have a typo. So this should be n. So p plus n. So this one is upper bounded by half log 2 pi e p plus n, and equality occurs when y is Gaussian. Equality is achieved when y is Gaussian. Okay, so if we want to make y to be Gaussian, then y x plus z, this is Gaussian, and I want to make y Gaussian as well, then x has to be Gaussian. So if we choose x to be Gaussian with the power p, and z is already given as Gaussian with the power of n, and this has a power p plus n. So basically, if as long as I choose x to be Gaussian, what I want to achieve can be achieved. Okay, so the equality is achievable by selecting x to be Gaussian distribution with the mean value 0 and power p as the variance. So by choosing this, we can achieve the capacity. So in this case, the input symbol alphabet should be the set of negative infinity to positive infinity. So that's the range of the random variable x, and the distribution has to be Gaussian. So so that's the capacity of the AWGN channel, and we can do certain easy exercises. Let's say P over N is 1 over 10 minus 10 dB. Then what is the capacity? And if you use the calculator, it comes out to be this. Okay, C is 0.0688 bit per channel use. And if we choose R to be 0.06 bit per channel use, and the user code, let's say length is 100, weight is 0.06, then you can come up, you can design a Gaussian code book with the 2 NR code words here 2nr is, n is 100, rate is 0.06, so it is 2 to the power of 6 code words. So you have only 32 code words, okay, in this code book, 32 code words in this code book, and the length of each code word is 100, okay. So when you design a code book matrix, you have x1 first code word and x1 first code word all the way up to x32 first xn 32, n is 100, okay, n is 100. So here the length is 100, you have 32 code words, and the alphabet of each element here is this, okay. So it is a Gaussian random sample. So each one is Gaussian random sample, and then you have 32 code words like that. So that's your code book. And then you have a 32 code words in your code book. Each code word has length 100. That's what we mean by Shannon code. You select these code words randomly, right? By selecting each element from the Gaussian distribution. Okay, so that's the random code book. Why do you have to use random code book? If you use random code book, the forward proof will be very simple. Okay, basically you can only condition upon sending the first random code word, and then you can select these other code words, randomly later on, after you have sent the first code word over the channel, and then you will receive y based on y100 based on first code word. These two should be typical, jointly typical, and all the other code words are not jointly typical with this. So that was the argument used in the forward proof, right? Remember that? So, how you are able to do that? Just by selecting the first code word and send, and be able to prove. Basically, that is based on random codebook argument, right? So these ideas using symmetries, random codebooks, and make the proof simple. Okay. All right. So that's the example. And then if what about if you use SNR, which is P over N, is like 1,000? What happens? Okay, 1,000 is 2 to the power of 10 approximately, right? Then the capacity here is half log 2 of in a ballpark, right? Approximately. Then half times log 2. So that's 10. So it's close to 5, right? 5 bits per channel use. So that's the capacity calculation. So this capacity can be smaller than 1. In this case, you can use for deep space communications, right? While you are using channels 100 times, you are sending only 0.06 bit per channel use, right? In this particular case, where your SNR is large, then you can send 5 bits per channel use, okay? So in this case, this is the case that signal power is significantly signal power is significant compared to the noise power. Then you can send your information at a faster rate. And then you can make the probability of error very small. But if you have a negative SNR situation, you talk slowly, and legibly. You send your message using channel code, then you can still make the probability of error very small. That's the idea. Okay. So the Shannon capacity over AWGN is described by this. So C is half log 2, 1 plus SNR. And this is bits per channel symbol, or bits per symbol, or bits per channel use, and so on. Okay, and basically the Shannon's channel coding theorem can be written this way. All weights below capacity C are achievable. Specifically, for rate R smaller than C, there exists a sequence of 2NR and codes with maximum probability of error converges to 0. And conversely, if you have a code whose maximal probability of error converges to 0, then the rate R must be smaller than C. Okay, so I think this one I should describe it later.